This section is called Gravity Near the Earth's Surface. And it's a little misleading because really the main part of this section, or the main point of this section, is really to look at gravity as a vector field. Now, we're going to have a little bit of fun here, but we're looking at gravity as a vector field. And the idea of a vector field is very, very important in physics in terms of we look at all points in space having a particular vector value to them. And for an inverse square force like gravity is, we can use certain concepts. One of them is Gauss's law, that as you look at the vector field itself through a surface, that becomes constant based on whatever mass is enclosed in that surface. Not a very common thing to go over in terms of gravity, but it's actually very common when we start looking at electric fields. So where do you generally see Gauss's law? You generally see Gauss's law as it applies to the electric field, but we're going to, sort of take a little bit of a sneak peek into the future and do a similar thing with the gravitational field. In any case, gravity. If we want to measure the strength of a gravitational field, we're normally looking at the acceleration of gravity, 9.8 meters per second squared near the Earth's surface. It does vary a little bit at the pole because the Earth is an oblate spheroid. The poles are closer to the center of the Earth than the equator. There's also a little bit of a difference in the acceleration due to the centripetal force of the Earth spinning. So we can't entirely attribute that to gravity, but you do weigh a little bit less at the equator than you do at the pole. In addition to this, we do know that the Earth is not a perfect sphere, other than it being an oblate spheroid. It also has differences in density based on if you're near a continental part of the crust or you're near an oceanic part of the crust. Continental crust is lower in density, tends to sit higher above the surface, where oceanic is denser and it sits lower. So this is going to also have some effect on the local gravity. Now, taking a look at some different maps, this is what the Earth would look like if we subtract off the effect of the higher gravitational field at the pole compared to the equator due to the oblate spheroid nature of our planet. And this is in mellogauss, these anomalies where the gravity is actually higher at some places and lower at other places. Don't get excited here. The difference is really, really small. A milligauss is actually, in terms of meters per second squared, it's like 10 to the minus 5 meters per second squared. So this is a very, very tiny, tiny difference, much, much less than 1%. But we can see that when we look at the gravitational map of the Earth, and this is not unexpected because we know that the gravitational force does depend on mass. And if there's denser material at some location, that's going to create a higher gravitational field there. Whereas if there is a lower density, you'll have less of gravitational field. Also, obviously, if there's a depression, that means that there's less mass there. If there is an elevated surface, as you see in Tibet, that'll also affect it. Not a geologist, so I can't completely interpret this map, but it is interesting to see that near the Andes Trench, where the Andes are, there is an increase in gravitational force. Around the Caribbean, there's a decrease. In the Hudson Bay, there's a decrease. And right here, along the mid-oceanic ridge, where we have a divergent plate boundary, we actually have an increase in gravitational field. So that's all going to be associated with different tectonic activities in these different regions. But overall, no matter where you are on the surface of the Earth, you're going to experience an acceleration of about 9.8 meters per second squared. And again, this acceleration is really the best way to measure the overall strength of the gravitational field. And again, here's just another view of that in a different type of projection. Okay, what would happen if we went inside the Earth? This is going to be part of our approach that we're going to do in just a little bit using Gauss's law. But if we could drill into the Earth, and quite honestly, our our ability to burrow into the Earth is very, very limited. We only scratch the surface, so to speak. So any holes that we've dug really don't take us to a low enough level where we're seeing any appreciable decrease in acceleration of gravity. But let's say that these science fiction movies like The Core or some of these other ideas where we could burrow into the Earth were possible. Obviously, due to a number of reasons, it just isn't feasible. What we would notice is that from the surface of the Earth, as we burrow down, we would actually experience a decrease in the force of gravity. Think about this. If I'm about a third of the way below the surface of the Earth, by Newton's universal law of gravity, the force is equal to Gm times m divided by r squared, but that's only considering if the masses were point sources. In this case, this red section of the Earth would be pulling me off into the right. So that would produce a gravitational force to the right on this diagram. The blue side, which is much larger and therefore would have a much larger gravitational force, would be pulling me to the left. Thus, I would experience a gravitational force still for the center, but actually my gravitational force should be somewhat smaller than it is on the surface because not the entire Earth is no longer pulling on me. Part of it is pulling me to the right, part of me is being pulled to the left, and that essentially produces a net force to the center, but lower than what it is on the surface. You don't believe me? Why don't we go to the center? Now we ask the question, where is Earth's gravitational field pulling me? Well, at the center, I'd have the right half of the Earth pulling me to the right, the left half pulling me to the left, the upper part pulling me up, the lower part pulling me down. It is weightless at the center of the Earth because there would be no down direction here. There would be, I'm at the center already. Where am I going to be pulled? So that's a very, very important point that inside the Earth, the gravitational field actually becomes less and less as we go lower and lower. It doesn't mean the pressure becomes less. The pressure is due to the overall overlying weight above me. So as I go deeper, the pressure still increases, but gravity as a force becomes lower and lower until I get to the center. Okay, so let's take a look at this in a more complete analysis. Again, we're going to use something called Gauss's law. And Gauss's law basically says, imagine we have the Earth right here, okay? The Earth, we're going to completely simplify it. We're going to say that it has a constant density. Its density is the same as at the center as it is at the surface. It is spherical, and we can visualize the gravitational field of the Earth as pointing inward. The acceleration is pointing toward the center, and that this vector field, as it crosses another spherical region, okay, this vector field, as it crosses, let's say, the spherical region up here, is going to be constant, and it's going to depend on whatever mass my surface has enclosed. Okay? This is a very, very important point. The vector g, which is the acceleration of gravity, when I integrate it over the entire surface, this is this outer spherical surface that I've surrounded the Earth with, is going to be constant. It is going to be negative 4 pi. G is the universal constant of gravity times whatever mass is there in the Earth. Now, think about this. Gravity does get less. We saw it with Newton's law, does get less as you get further and further away. But if you think about it, this sphere that I have that's surrounding the Earth, as I get farther and farther away from the Earth, the sphere, its surface area goes by 4 pi r squared, is getting larger. So as the area gets larger by r squared, to keep the right-hand side of the equation, g has to drop off by 1 over r squared. Okay? Again, sort of a unusual approach for the gravitational field. This is really something that we see more with electric fields, but this is known as Gauss's law, that the flux of this field, okay, across the surface is going to be constant. And it's going to depend on how much mass is enclosed. For electric fields, it's how much charge is enclosed. Okay, so here's Gauss's law for gravity. Okay, sorry, Gauss, if you never intended it that way. But again, let's say I surround the Earth with this sphere. Okay, the Earth's volume is going to be 4/3 pi r cubed. This sphere itself is going to have an area of 4/3 pi r squared. By the way, I apologize for this. This r cubed, this should be big R, not small r. Big R is the radius of the Earth. Small r is the radius of the sphere that I'm putting around it. And here I'm again going to eventually integrate this vector over the area, negative 4 pi gm. Mass is related to density. Density is mass divided by volume. So mass is volume times density. So I'll make that little substitution right here. My volume of the Earth, and I did get it right here. My volume of the Earth is 4/3 pi big R cubed. Okay. So now 4 times 4 is 16. Divide that by 3. So that's a 4/3. Pi times pi is pi squared. R cubed is just dropped in here times rho. And here's another version of my Gauss's law, not in terms so much of the mass now, but in terms of rho, which is the density of the Earth, and r, which is the radius of the Earth. Okay, so I have this uniform sphere. I'm going to integrate over this uniform sphere. I assume that at some distance, small r, all the gravitational field is the same. That g is a constant, so that can go out in front of the integral. I integrate over the entire area, which is just, again, 4 pi r squared. That's the area of this bigger sphere right here. The smaller sphere, again, is Earth. On the right-hand side, I have big R, which is the radius of the Earth, rho, which is the density of Earth, and these other constants. So now I can simplify things a little bit. I'll divide both sides by 4. So 16 divided by 4 is 4. The 4 goes away here. I'll divide both sides by pi. I'll divide both sides by small r squared. And we get that g, the gravitational acceleration, is equal to big G times 4 pi big R cubed times rho. Remember, 4/3 pi R cubed is the volume times rho gives me the mass. And I just get back exactly what I got back when we did this with Newton's universal law of gravity. That G, small g, the acceleration of gravity, at any distance small r is equal to negative g times the mass of the Earth divided by r squared. So Gauss's law does hold for any distance r. Again, using Gauss's law is a little bit, strange when you first see it, because you're actually creating a sphere at some distance small r. As long as that sphere is uniform to whatever it's surrounding, you can do the integration very, very easily, because small g here is a constant. And, when I integrate over an area, I'm just getting the area back itself. So outside the Earth, we get the same result that we saw before. Okay? Now, here's where Gauss's law is very, very powerful. Looking inside the Earth, we could integrate the infinitesimal amounts of mass for the Earth and come up with our gravitational force. This is sort of what we did in our head. In this case, we said we have this much Earth to the right, this much Earth to the left, to find out what the gravitational field is at this point right here. We could do that integral, but it would be very, very difficult. The beauty of Gauss's law is it only worries about the mass that it encloses. So if I go inside the Earth, where big R is the radius of the Earth, Small r is my distance from the center. So if I'm 2/3 of the way toward the surface, like I had in the previous example, small r here would be 2/3 of big R. Okay. So now I want to know, what is my gravitational force at this location, small r, inside the Earth? Remember, we've already determined via symmetry that it has to drop to zero at the center. Okay. I want to know what it is at some distance r there. So again, we're going to do Gauss's law. On the left-hand side, nothing changes. We have G dot dA over here. And because G is going to be constant all over this smaller sphere, this sphere inside the Earth, we simply get GA, G's constant goes out front, we integrate over A. And again, this area right here is 4 pi r squared. That hasn't changed at all. However, on the right-hand side, I'm no longer using big R. My mass that I enclose, okay, is just the mass inside that inner sphere. And the inner sphere has radius R. So now my new mass is 4/3 pi r cubed, small r cubed, that's my volume, times my density, and that gives me my mass. Okay? So I solve for this. Now there's no big R. I can cancel out some of the R's on the left with the R's on the right. Again, I'm going to divide both sides by 4. So 16 becomes 4 in the numerator. 4 goes away here. I divide both sides by pi. So pi squared becomes pi. But now notice that this r squared, I'll divide the left-hand side by r squared, the right-hand side by r squared. R cubed divided by r squared becomes r. And what we see here is that G, the acceleration of gravity when we're inside the Earth, okay, is equal to some constant, negative 4/3, negative because it's pointing toward the center, negative 4/3 G pi. Rho is also, we're saying it's constant density, okay? We'll change that in a little bit. But the gravitational force is proportional to the distance from the center. So when r goes to 0, just as like we expect, the acceleration of gravity also goes to 0 at the very center. Okay? So looking at this overall, what does this mean by the acceleration, about the acceleration of gravity? Well, inside the Earth, the acceleration of gravity is proportional to the distance until we get to the surface. And that's where, if the Earth were a constant density, we would expect the gravitational force to become the maximum. Once we leave the surface, however, our Gaussian sphere is getting bigger and bigger by r squared. So our force, our acceleration, is dropping by 1 over r squared. And that's exactly what we know to be true for Newton's universal law of gravitation. So again, that's just a really neat way of looking at gravity in the context of Gauss's law, which is more commonly applied for electric fields, but they're both 1 over r squared type fields. They're both inverse square fields, and Gauss's law will work for both. Okay, what about the real Earth? What happens when we're dealing with a real planet, which is differentiated because we know the iron core is denser than the mantle is denser than the crust? How does that affect our results? Well, if we do Gauss's law for that, we actually have to do, sort of a shell by shell integration. And what we find out is, if we say, well, the inner core has a density of 12.8 to 13.3 grams per cubic centimeter. The outer core is between 9.9 to 12.2. The lower mantle is made of dense, very mafic rock, 4.5 to 5.6 grams per cubic centimeter. The upper mantle a little bit lighter, mostly olivine. I'm not a geologist. Don't kill me if I'm not completely spot on this. And then the crust is, of course, the lowest density. So that means, as we concentrate a tremendous amount of mass toward the center, especially in the core, and not as much in the outer part. And what we see is a slightly different profile. Again, Newton's universal law of gravity holds above the surface. It drops off by 1/r squared, but it actually almost sort of creates a plateau in the mantle because as the density is increasing, it's increasing fast enough to hold off that linear uh, that linear decrease at which we would have thought about. But again, it almost becomes linear again once we get to the core. But eventually, when we get to the center of the Earth, the acceleration of gravity is going to go to zero. Okay. All right. So let's have some fun. If we could drill all the way through the Earth, let's say we can make this hole or this elevator shaft that could go all the way from one side of the Earth to the other, right through the core. I think they did a remake of Total Recall where they had something like this. Again, totally preposterous because, as you dig deeper into the Earth, the rock becomes plastic, and any hole that you try to dig would simply fill in, and nothing could withstand those high temperatures as you went deeper and deeper. But let's say that we can do this. What would happen if you jumped in that hole? Okay, and just to make this even more preposterous, let's say there was no air resistance as you fell through that hole. Well, if you fell into that hole, what would happen is you would fall toward the center of the Earth, but at the center of the Earth, you would regain equilibrium, meaning that the forces would be zero and nothing would be affecting your motion. So you accelerate toward the center, you now have a high velocity when you reach the center, but then there's no forces to slow you down. You would start falling to the other side and you make it all the way to the other side of the hole. In fact, you would continue, again, we're getting rid of air resistance. Let's say that you were in a spacesuit and this was evacuated and you fell, you would oscillate back and forth, and make it to the other side of the world, and oscillate almost like a harmonic oscillator. It would take you approximately 42 minutes to make it to the other side. And if you fell back to where you started, that'd be another 42 minutes. So, roughly, just a little bit under 90 minutes to make that. Now, what's interesting is that if you orbited the Earth, and we calculated the time to orbit the Earth, if you're orbiting right over the surface of the Earth, again, ignoring that we had any atmosphere, that would also take you about 90 minutes to make that round trip. So again, not really useful for anything. Nice little thought experiment, but essentially falling through the Earth is almost like having an orbit around the Earth. And again, your period of the orbit would match pretty much what a satellite would be orbiting if it was orbiting right above the surface of the ocean, approximately 90 minutes. But again, that wasn't really the purpose of this section right here. Again, the purpose of this section was to, sort of look into the future, if you will, and sort of see how inverse square laws obey this concept that Gauss came up with, which we know as Gauss's law, which becomes a very convenient way of simplifying a calculation of an inverse square type vector field.